Okay, so welcome to session 3BB at GSE 2021. Your next session will be provided by Dan Wiegand. You can correct it later. And Dan Rosa. I had more luck with that one. And this session is on reducing the root cause problem determination time by analysing anomalous behaviour. Again, just to remind our charities this year, if you can donate generously to these worthy causes, lifeboats and guide dogs, and allow yourself entry into the raffle. You just never know, you may be rewarded for your generosity. You can see it as appreciation for the time and effort spent by our presenters at the conference this year. Okay, any questions, you can put them in the chat. You will be allowed to unmute at the end, but any questions, put them in the chat, and Dan will respond. Okay, so with no further ado, over to you, Dan and Dan.
All right, thank you so much, Anna. So my name is Dan Wiggins. I'm one of the product managers responsible for the solutions that we'll talk about today that are new to IBMZ and extremely powerful. And with me, I have Dan Rosa, who's one of our ZOS developers that's going to walk us through an in-depth demo as well. So just to kind of level set back to what you might have seen at the beginning of the conference last week, when a peer of mine, Domenico Delterio, talked about the journey to AIOps. And the solution that we'll talk about today fits squarely into this, really in the decide phase. So those three phases, again, are detect, where we can look at hybrid infrastructure and applications to detect issues and anomalies. And decide is really getting down to helping us isolate problems and identifying root cause so that we can take action and actively respond to any issues that we find. And really, we're trying to drive a lot of AI across all of our solutions. And we'll really see this within the solution that we'll talk about today. So if we break down into the decide phase just a little bit, and that's really where the focus is getting down to root cause. The session today will focus on anomaly correlation, where we can identify short-term anomalous behavior across the ZOS subsystems. And what this really helps us quickly do is identify all of those cause and victim relationships. So if we're seeing a slowdown in KIX transactions, it may not actually be KIX that is causing us the underlying issue that's there. So we'll see how this technology works today and how it takes a novel approach at solving some of the business challenges that we've had and seen. So in terms of the overall AIOps workflow, again, being in that decide phase, we're really looking at reducing the mean time to identify. And again, if we're looking at understanding the relationships between KIX and what's running on ZOS and maybe DB2, this will help us get down to that near real time for mean time to identify. And then once we have that, it's always going to take a little bit of time to, okay, we understand what the root cause is. Now we need to go and do a little bit more diagnostics to understand really why this is happening. So this is the potential impact that we're seeing with this solution as one of the tools in our toolbox. So let's start with why we just built this solution to help our IBMZ clients. If we take a look at what a lot of our workloads look like today, IBMZ is really a black box. And we may know that we have KIX running on this LPAR and DB2 running on this LPAR, but how those resources are being shared and how all of the different activities that are running within those environments and their interdependencies is really a lot of things that our clients don't have a clear understanding on, and how those things tend to impact each other. That's really why we built the solution that we'll talk about today. So if we have workload performance issues, the biggest challenge that we have in doing that diagnosis really is in data and data itself. And there's really three reasons for this. First, data is costly. To collect a large amount of debug and trace data, it takes a lot of CPU and a lot of storage to collect and analyze that data. Next, data is siloed, so we can turn on CICS 110 transaction records and we can get an awful lot of information there, but we don't see what's going on in DB2 at that same time, or what's going on in the OS, or what might be going on in IMS or MQ. We only really get one piece of that puzzle, and it really makes it a challenge to do a lot of that data correlation. And lastly, data is noisy. So thinking back to turning on those CICS 110 transaction records, there's an awful lot of data and information that gets generated. And in many cases, it's too detailed or to really get down to finding that root cause. So it's finding that proverbial needle in the haystack. So really, data has been a big challenge in kind of diagnosing a lot of these workload performance issues. For a number of years, we've had RMF data available to us, and this is an extremely rich sort of source of data, but it's really not beneficial for or sufficient for identifying root cause of operational issues. And one of the biggest reasons for that is the very infrequent sampling of RMF. If we're looking at 15-minute intervals of time, any of those little small transient performance issues that might occur during a 5-second window during that 15-minute interval will just get summarized out within that entire period of time. So we really miss those very short transient issues. So RMF data still is extremely valuable. It's still used by a lot of our performance and capacity analytics solutions, but it's just really not well suited for what we have in looking at these kind of short-term performance issues. So this is why in January, March of last year, IBM introduced two new components. The first one is the ZOS Workload Interaction Correlator, and this is purpose-built data, and this is all meant to solve that data problem that I talked about. So this is building standardized, synchronized, smarter data that's generated every 5 seconds. And it's built to be high-value data with low cost. And we have support today for generating correlator data through the ZOS Supervisor, CICS, IMS, and DB2. So let's start taking a look at kind of what this means in those terms I described. So first, we solved the frequency problem by generating data every 5 seconds. So every record that gets generated for ZOS, for CICS, for IMS, and DB2 are on that exact same 5-second clock. So we're generating all of those short-term interval data points. So that's the synchronized part as well. So we have that, again, on that exact same clock. The data is built such that it adheres to a certain pattern. So it all defines on what activities are running within the system, and those are organized across a set of what we call software stacks or job cubes. And those cubes are identified by core type, job size, or job priority. So core type being on the core processors or is workload running on zip. By job size, are we looking at a tiny job all the way up to our largest pieces of our workloads? Or job priority, is this something that's running as a discretionary job? Or is this critical? And what this allows us to do is take all of this short-term activity data and analyze this through our Workload Interaction Navigator, which I'll introduce next. So we can look at our entire workload stack within a single analytics engine. And this is where we have the Workload Interaction Navigator to take a look at. So this is our single interface to analyze all of those data points coming from the correlator. Now, one of the things that we talked about in generating that correlator data was performance. And through all of the ZOS measurements schemes that were done in performance, it was undetectable the overhead that was needed to generate the SMF98 records. So we have a lot of rich data that can be generated with little to no CPU overhead, and it's only generating a small number of megabytes or gigabytes of data in a single day for various subsystems. So a very small footprint. Again, it's being that purpose-built data. In fact, the IBM had put out a flash or announcement saying that we do recommend that all of our clients turn on the SMF98 subtype 1 records because it's fantastic for first cause problem identification. And I do have the link to that flash later in the presentation that we can go out and refer to. So once we have all of this data, we have our navigator, which is our UI, to look at all of this information. It runs as a Zoe application and is quite an intuitive and useful interface. It does a lot of that intelligence and heavy lifting up front. So what this will do is take a subset of correlator data, say maybe over 15 minutes, and look for all the different anomaly points in that. So it'll establish a baseline for each different activity that's running and look for those high variances where it's outside of that normal baseline. So we might see this be identified by a spike in CPU utilization or a spike in transaction response times that happen during certain points. And what this will do is take a look at all of those different anomaly points and correlate the ones that have that same pattern into activity groups. This is how we start to group all of the different things that are running that are experiencing the same kind of behavior. And this is really the power that lets us identify those cause and victim relationships. So this is how we get to identifying, those little peaks and valleys and temporally correlating all of those activities. What the UI will also do is bring the most important things up to the front. So if we have things that are running in our critical workloads, our large jobs, or our global things that are running, it will bring those up first and try to identify the most important things that are running within the environment. So what can this be used for? First and foremost, and really the focus of what we'll see today, is identifying those cause and victim relationships. As we get into the demo with Dan here in just a couple of minutes, we'll see that we can identify maybe something that's happening within Kix, but that's caused by something else. Or DB2 is another example that we have that's not really going on with DB2 and starting to correlate a lot of the key DB2 activities. The other thing that we can do is compare two different time intervals so that we can view any potential changes we want to make to the environment to make sure they have the desired effect. So think of this as kind of proactive change verification. So we can look at changes across hardware, if we want to maybe upgrade DB2 to a new version and apply maintenance. We can make sure that with the snapshot that's running, that things are running now as they were before. If we do this in a pre-prod or sandbox environment, we can kind of see the impacts of what's going on within those environments. So with that, I'm going to go ahead and stop going through the slides here for a moment. I'll let Dan drive through the demo. In a lot of cases, seeing is really kind of believing. It puts a lot more context around what I've described. And then I'll come back and talk a little bit about a couple of the key use cases that we've been able to use this for, as well as kind of tie up some of the other things and how this compares to what we're seeing with anomaly detection within our other machine learning solutions as well. So Dan, I'm going to go ahead and stop sharing and let you grab the screen share.
Thanks, Dan. Let's see. Can you guys see my screen?
We can.
Okay, thank you. So let's see, I'll check the chat. See if I didn't see any questions in the chat. So we will keep going through the demonstration. So my name is Dan Rosa. I work in the ZOS dispatcher component. The ZOS dispatcher is involved in providing access to CPU for every work unit on the system that's ready to run. Excuse me. This whole project really, started about 5-6 years ago now, and the first piece of the solution was delivered called high frequency throughput statistics. And, this whole project started because of one of the responsibilities that I have is that I have to run the ZOS workload to efficiently use the hardware cache on every machine that's delivered. And the hardware guys change the cache on every machine. So we're always tuning the hyper dispatch algorithms for every machine to most efficiently use the hardware cache that's available. And hyper dispatch has to make decisions at a very fine-grained interval, right? It's got to make decisions in, the seconds range to get the workload to run well. And so when we started looking at the data that we have to try to get the workload to run more efficiently, as Dan Wigan was pointing out, we have RMF, we have long-lived intervals, but we really don't have, frequent summary data that's generated about how the workload is running. And we need to be able, hyperdispatch needs to be able to detect transient anomalies in the execution of the workload so that we can run it, so we can eliminate those anomalies and use the hardware cache more efficiently. So we built this new technology called high frequency throughput statistics, which was built about 6 years ago to generate this 5-second data generation. That was SMF98 subtype 1 that any client in the world can go and turn on. And then we built some tools on top of it to be able to analyze that data, get insights into what was happening in the workload. And so that helped us to do our hyperdispatch jobs better, but it also opened the door up for us to do general analysis on the workload, right? Hyperdispatch, we had to become general performance analysts to understand how the workload was running. So it became, a natural follow-on to that says, well, we can also start analyzing workloads that we've never seen before, whether that be IBM workloads or client workloads. And we have this 5-second data generation that no one else has, plus a analysis engine on top of it to be able to identify and correlate anomalies. So we could see things in the workload that nobody else could see because we had data that nobody else had. And then we started to say, well, geez, if we can become general performance analysts and get this insight with our own data from ZOS Supervisor, would it be great if we could broaden this technology to be something that other ZOS components of middleware could plug into to generate their data, and then have the same analytics engine go off and just analyze data across the ZOS stack. So that ended up turning into the correlator navigator, which we started developing about 4 years ago. It GA'd about a year and a half ago. The first correlator navigator pieces GA'd, and over the next year and a half, we had subsystems coming in to exploit correlator data generation. So KICS supported correlated data generation, then IMS. And most recently, a couple of weeks ago, we had DB2 be able to plug into navigator analysis of their data. For DB2, we did something a little bit different. DB2 generates SMF 100 records. It was just easier from a DB2 perspective, and because DB2 has different characteristics than KICS's and IMS's, where we could turn the SMF 100 records and generate those in a 5-second interval and feed those into the navigator for analysis. So we delivered that support, and now we've got some pretty rich capabilities between the navigator and the correlator to be able to analyze and detect anomalies vertically across the ZOS stack for a single system, as well as horizontally across systems in a sysplex. So I get involved in crit sits to help diagnose root cause of client performance problems, and often using the navigator on just SMF98 subtype 1s to help us to hone in on the root cause of what the problem is. So I'm going to take you through some demos today about how we can use the correlator navigator to identify and correlate anomalies, and give you guys some insights about how we use this technology in the lab, and how you have an opportunity to use these technologies at your client sites as well to help diagnose transient problems in your workload. So we're going to start taking a look at, well, these are all IBM lab data, but this first set of data happens to be from 4 systems in a sysplex, and we're analyzing data from ST Lab 20 through 25, 29, and Baker 7. In this data that's been sent to the navigator for analysis, we have DB2 data as well as EOS supervisor data. We have 1 hour of data from 1300 to 1400 across 4 systems. We happen to be looking at ST Lab 22, and we have information about the CPU configuration. We can see that there are 9 vertical highs, 2 vertical mediums, and a few vertical lows running in this particular system for this 15-minute interval. So navigator analysis by default brings you into looking at a stacked graph of CPU utilization. So Dan Wiggins' charts, he had the cubes, and one of the dimensions of the cubes was job priority, which had values of discretionary, low, high, and critical. And we present the CPU utilization as a stacked graph by job priority. So you can see that there is, looks like some discretionary priority work down here, as well as some low priority work and some critical priority work. So we're looking at, the navigator analyzes 15 minutes worth of data to detect anomalies and correlate them. And we happen to be looking at the first 15-minute interval from 1300 to 1500. And the navigator lets you go and navigate different 15-minute intervals, so we can change what 15-minute interval we're looking at. You can see the CPU utilization changes. You can also change the system you're looking at and pick a different system. CPU utilization changes as well. So it's really easy and handy to navigate around in the data for what for what you're looking for. The graph itself, you can hover over the graph and you can see what the CPU utilization is every 5 seconds. So correlator does do 5-second data generation, and you can hover over the graph to see what the CPU utilization is at every 5-second interval. The really powerful function that is in a navigator is this function that we call automated analysis. And automated analysis just does a lot of heavy lifting to crunch the data to figure out what is anomalous in the data. It correlates the anomalies in that data, and it presents it to an analyst. So if you dig into exactly what it does, the navigator will establish a baseline for every activity that it has across supervisor, KICS, IMS, DB2. It will identify anomalous peaks that significantly deviate from normal. It'll temporally correlate those impactful anomalous peaks into correlated activity groups, and then order and prioritize each correlated activity group and its activities. So those activities happen on every system in the sysplex. So we've got 4 systems where that analysis and correlation is done. And then once that's done, the navigator will go and take every system in the sysplex, and it will temporally correlate the correlated activity groups into system lists, and then order and prioritize the system lists in our correlated activity groups. So the net of it is by the time the analysis is all done, the navigator has created an organized progression of anomalous, impactful, interacting activities with the worst offender that the analyst is going to go take a look at for this 15-minute interval and say, okay, what anomalies of significance are in this data, and go and diagnose, what's happening behind those anomalies. So in this particular after automated analysis is completed, the navigator found 14 activities worth analyzing across this 15-minute interval across those 4 systems in a sysplex. We happen to be taking a look at correlated activity group 1. So this is the first set of anomalies that are correlated. And we are looking at a system list. So the system list says it's 1.1. So a system list is a collection of anomalies that are correlated across systems in a sysplex. So system list 1 is the first set of anomalies, and the second one in the 1.1 signifies the first system in the system list. So we're looking at the first group of anomalies occurring across systems in a sysplex, and we're looking at the first system that has those anomalies. So the navigator updates the table below with all of the anomalous activities it found that are worth analyzing. This first anomalous activity group has 6 activities. You notice that there's only 4 entries in the table, and that's because the navigator does some reduction of the data. And the reduction of, there's a number of factors it uses, but the navigator will contract activities that look alike because the navigator says, well, it just looks similar, so I'm not going to show this lesser important activity. The navigator will also hide activities that are very, very insignificant in the workload. So because of the cube chart that Dan Wigan presented, we have a concept of what's happening across the whole workload. We have a concept of what's happening in every one of the cubes. So you can understand what portion of an activity, is what part of the whole any activity is relative to the whole workload. So as an example, you could say, well, this particular cube has 20% of the activity across the entire workload, and that is significant in the workload. If you have something that's 0.5%, well, that's less significant, and the navigator will say, well, I'm not going to show you this by default because it's insignificant in the scheme of the whole workload. So the navigator has checkboxes that you can use to bring back those activities that the navigator has hidden for you. We're going to check one of those checkboxes to bring back the rows that the navigator contracted. So those are the activities that the navigator that look very similar in their graphs. So we're just going to look through each of these activities one by one, just to show what the navigator is doing. So I'm going to click the first row to start looking at the first activity that the navigator has found. That first activity is called suspend contention time, and when you click an activity, it graphs that particular activity across the 15-minute interval in the graph. So it showed up as the yellow line up here in the graph. And in the graph itself, there is a red vertical bar that is the correlation point that resulted in this activity being included in the correlated activity group. So the red vertical bar goes through the anomaly that resulted in this activity being included in this correlated activity group. And the activity name itself is suspend contention time. And if we hover over the graph, we can get some more information about what that activity is, and its and some more details around what's happening at that anomaly. So we have a peak in suspend contention time that is occurring at 13:04:00, and we can see in the hover text in the table that popped up that that there is system resource contention going on, and that system resource contention is on the top suspend lock name of CML. And if we look down at the second group of entries that are listed in orange in the table, those indicate the job that was driving contention on that resource. So we can see the consumer job name of DL71 DBM1. And what this graph actually contains is it actually contains two lines of graph. There's a yellow line, which is suspended contention time, and there's an orange line, the consumer suspended contention time. But what happens is that the yellow line is graphed on top of the orange line because they have exactly the same pattern across both of them. So one of the things that we've done with the navigator is we've infused the navigator with subject matter expertise knowledge. So as an example, whenever suspend contention time pops up as an anomaly, an analyst wants to know, well, what job was driving that suspend contention? So this is part of the subject matter expertise that we've infused in the navigator so that an analyst could get an answer to those commonly asked questions whenever a anomalous activity pops up. So basically the takeaway from here is that at 130400, there is system resource contention on the CML lock in the DBM1 address space. So then we're going to click the next button to go to the next anomalous activity, which is global spin contention time. This activity is also from ZOS Supervisor. You can quickly see which activities are from which ZOS component or middleware by looking at these dots on the left side. So the supervisor dots are this greenish color, and those indicate supervisor activities. You can see down here at the bottom, we have some yellowish dots. Those yellowish dots are DB2 data. So we're looking at another supervisor activity. This activity is also from ST Lab 29, just like the previous one. All activities we're looking at in this correlated activity group are from ST Lab 29. And the activity name, global spin contention time, says that there is system resource contention going on at this particular time as well. We hover over the graph and we can see at 130400, it's the same time that we saw in the first activity. That's where the red vertical bar is located. And we can see that there is contention on the RSM XM lock, and that contention is being driven by the DL71 DBM1 address space. So DB2 is driving contention on the RSM XM lock as well. So there's system resource contention going on another resource at 130400. So click the next button to go to the next activity, which is subsystem lock requests. This is from DB2, and it's from DB2 member DL71. You can see over here on the right side that DB2 member DL71 is the data sharing group DSN L7. And it says that there is an anomaly peak in subsystem lock requests at this red vertical bar. We'll hover over it and say, look, it's 130400. There is a peak in subsystem lock requests. What's interesting is that if I back up 1 5-second interval to 130355, we can see that there are no subsystem lock requests being done at this 5-second interval. So this is suggesting that something is happening in the workload where there's no DDF transactions that are flying around at 130355. So this particular workload is running, it's running DB2 distributed workload that's doing DB2 DDF transactions to access and update that data. And we can see that that's unexpected, right? This particular workload we're running in the lab, it's just supposed to be running DB2 DDF transactions more or less continuously. And we've got a 5-second interval where there was no DDF, where there seems to be no DDF transactions going on because there were no subsystem lock requests made at that time, and you would expect contention to be, you would expect there to be lock requests made for making updates for DDF transactions. So click the next button to see the next activity. And the next activity is DDF commits. And DDF commits, if we hover over the graph, we can see that the anomaly peak occurs at the same time, 130400. And here you can clearly see the two lines in the graph. There's a yellow line, which is for DDF commits. And there's an orange line for DDF DBAT's high watermark. So again, this is about infusing the navigator with subject matter expertise. And whenever you have DDF commits, you want to know, well, how many DB2 database access threads or DBATs are driving those DDF commits. So we have the DBAT's high watermark that is shown as well on the graph. And we get those two pieces of information just by hovering the mouse over. If we get to the peak, we can see that there is a peak in DDF commits. And the DBAC high watermark is about 132. So what's interesting in this data is you can see that the high watermark for DBATs has stayed about the same, but we have a surge in the DDF commits. And that's good to know because it says, all right, well, it's about the same number of DBATs that are driving through more DDF commits than normal. If we back up 1 5-second interval to 130355, we have this same signature where there are no DDF commits, and the DBAT's high watermark is 0 at this point. So it says that it's more information that there are no DDF transactions running at this particular 5-second interval. Click the next button to get to DDF connections. And DDF connections, hover over the graph. This is also for DB2. All of these DB2 anomalies are from the same DB2 member, all from obviously the same DB2 data sharing group. Hover over the graph, and we can see that at 130400, we have another peak in the DDF connections. So there are more DDF connections that are coming in at 130400. We also have the orange line, which is the connections high watermark that occurs at the 5-second interval. We back up a 5-second interval, we can see that there are no DDF connections, and the DDF connections high watermark is 0. So the connections have apparently disappeared at 130355. So that's another indication that says, hey, there's no DDF work running, there's no connections, there's just nothing going on at this 5-second interval, which is not expected in this particular workload. So I'm just going to check the chat, see if there's any questions. I don't see any. And next, we're going to click the next button again. We'll just take a quick reminder. We're looking at ST Lab 29 here. When I click the next button, we're going to go to correlated activity group 2, which is from system list. It's in system list 1, and we're now looking at the second system in the system list. So we changed systems from ST Lab 29 to ST Lab 22. And we've got a little quirk in the navigator where that check mark didn't carry over to the next activity. That we've got to go fix. But the navigator here is showing that there are anomalies occurring at a second system in the sysplex at the same time as the anomalies we saw on the previous system. And just taking a look at the first activity, it's suspend contention time, and we hover over the graph, and we can see that there's contention. The contention on suspend contention time was happening on the CML resource. And we can also see that the consumer job name, in this case, was DL74 DBM1. So the previous system was DL71 DBM1. This is DL74 DBM1. So it's a different DB2 member. And we'll see what data sharing group that it's part of when we get to the DB2 analysis. But none of it is that we could see that there is also system resource contention going on a CML lock on another system in a sysplex, also driven by a DB2 member occurring at the same time, which is great information to know because when you're analyzing a problem, you often want to know, well, is the problem I'm looking at system in scope or is it sysplex in scope? And the navigator really helps you to determine that very quickly, because if your problem is sysplex in scope, you're looking in different areas than if you're looking at a problem that's system in scope. So having that piece of information, saves time when you're trying to diagnose the root cause of one of these transient performance problems. So I'll click the next button to go to the next activity, which is global spin contention time. Hover over the graph, we can see 1304.00. There is lack contention on the RSM-XM lock driven by the DL74 DVM1 job. So again, same system resource contention that we saw on the previous system occurring on system ST Lab 22 at the same time. And we'll click the next button to get to the final activity, which is subsystem lock requests. Subsystem lock requests. Now this is a DB2 activity. We're looking at, this is from the DL74 DB2 member, and it is in data sharing group DSN L7. So it's the same DB2 data sharing group that we saw in the previous system. And if we hover over the graph, we can see that this particular anomaly for subsystem lock request happened at 13:04:05. So it's actually 5 seconds after all of the activities we saw previously, whose anomaly occurred at 13:04:00. The navigator considers anomalies correlated if they occur plus or minus 1 5-second interval, because there can be anomalies that are trailing anomalies and leading anomalies. So we want to be sensitive to anomalies that occur around the same 5-second interval. So we can see that this peak in subsystem lock requests occurred at 13:04:05. If we back up a 5-second interval, we see no lock system requests at 13:04:00. And no subsystem lock request at 13:03:55. So the navigators say, hey, 13:03:55, there's really no DDF transactions that are running at this particular point in time. And that happened across 2 systems in a sysplex. So the next step would be figuring out, well, why are there no DDF transactions? You'd have to go to the next, a reasonable next step to diagnose this particular problem would be to look at the DDF clients to find out, well, do the DDF clients have transactions outstanding at this particular point in time? The answer is yes. Then that's interesting. Why did the connections get dropped? Probably the answer is no. Probably the connections were lost for whatever reason. Maybe the client's disconnected for some reason. And we could see in the data that there was a signature that there were no connections from DDF clients and then a bunch of connections. So it suggests that DDF clients went away and then came back. So you could go look at the client data to figure out, well, did that in fact happen? So the purpose of this demo is really to show that the correlator navigator can identify and correlate anomalies vertically across the ZOS stack and horizontally across systems in a sysplex. The navigator has found 2 DB2 instances on 2 different systems that process no DDF transactions at 13:03:55. And then at 13:04:00, DB2 received a burst of DDF connections, as well as DDF transactions started flowing once again. So you have to figure out, well, why were there no DDF transactions flowing at 13:03:55? So that's kind of what the navigator does in terms of its anomaly detection and correlation. The real other important factor is, well, when would you do this analysis? And out of it is that there are a lot of performance monitoring tools that are out there. There are certainly people watching their systems to verify that their systems are running well. There are users that are using these systems and often reporting problems. So there's a number of different channels where a performance problem can pop up. It could pop up from users. It could pop up from a dashboard. It could pop up from a monitor. Doesn't really matter where it comes from. But if you have a reason to go and investigate what is behind a transient performance problem, Navigator is very useful in helping you to identify where to look and when to look. So where to look is often, which ZOS or middleware components to go take a look at. When to look is 5-second granularity to when the problem occurred. We've been able to use this data in client analysis as well as lab analysis to be able to differentiate some anomalies as well. There's times where you have anomaly signatures pop up, and then there are fallout from that particular anomaly that occurred, and you can differentiate, what was the first anomaly domino that really started the chain of dominoes to fall over. And it's just really useful to help an analyst focus in on the root cause of that performance problem. Navigator itself and a correlator is generating data every 5 seconds. So the navigator and correlator don't know everything. Navigator is just trying to get an analyst closer to defining the root cause of the problem. Oftentimes when you have anomalies identified in the navigator, you have to go look at component details around what to actually define what the root cause of the problem is. But the navigator helps because the navigator says, well, I told you which ZOS components and middleware to go look at, and I also told you when to go look, this 5-second interval. So there are a lot of times in crit set analysis that I'm involved in where, sometimes clients have to go recreate, collect additional data, send it to IBM. And it's really constructive to be able to have a navigator to say, look, the anomaly signature occurred in this recreate. Okay, good. Now I know what time to go look at the component detail for things that are going on at that particular 5-second interval that isn't good for that particular component. You can also use it as a technique to say, well, look, the transient performance problem didn't occur in this set of data. Well, I don't need to go look at the component details because I'm not going to find anything interesting in that data. Maybe I could use it as a base for when things are running well, but I can't use it to try to go find what's anomalous in the data, in that component specific data. So Navigator really helps, an analyst define the root cause of a problem more quickly than they could before, because the Navigator helps to get an analyst looking at the right data at the right time to diagnose the problem. So with that, I'll stop talking for a bit and check the chat and open it up for questions. If there's no questions, I have some more demos that we could go through.
Okay, so there are no questions in the chat. I don't know, Dan won. If you needed to follow up with something.
I don't see any questions in the chat, so maybe you can see something I can't see.
No, there's nothing in the chat.
Okay,
Yeah,
all right.
I have a couple of slides to go through to kind of close up and wrap up the session.
And there is now actually a note in the, I'm not sure whether it's a question or a comment, but ZWIC and ZWIN are licensed. I thought I heard ZOS 98.1 are available free.
Yep.
Yeah,
so I can I can answer that one. So as we sit here today on I guess November the 10th. So the correlator is a chargeable component. There is an announcement coming out next week where we expect the correlator to be included with RMF. So that will be part of that. So and you're absolutely right. Today the supervisor records, the 98 subtype 1s, are available free. So you can go and turn those on today. So the records that you'll be able to use if you're entitled to RMF in the very near future are the KICS, the IMS, and the DB2 records. The Navigator, which Dan had taken us through, is licensed software, um, but it is something that we can certainly work through a POC, and there's some additional work coming out soon. We'll have a Z trial available very soon. We're going through the final kind of user testing as we speak. So that should be out and available within the next couple of weeks as well. So a lot of new things that are coming out around the correlator and navigator over the next week or so.
Yep, that's great, Dan. Yeah, certainly, Dan Wigan and I, are very, very interested, working with clients on correlator navigator proof of concepts. I mean, it's certainly more exciting to see your own ZOS data when you see your own ZOS data analyzed through the navigator and getting insights about anomalies that are going on in your workload that you might not even know are occurring. And it's always fun for us to do analysis on client workloads as well. So if you're interested in a correlator navigator proof of concept, I mean, talk to Dan Wigan or myself, and we'll see. We'll work through what would be interesting from a correlator navigator proof of concept for you.
Yeah, and yeah, so your local IBM account team will be able to certainly help as well. So I did want to spend just a couple of minutes as we wrap up this session on just a couple of differences in what you might have seen with our other anomaly detection solutions. So just kind of comparing what we see with the workload interaction navigator and our Z anomaly analytics with Watson. So Z anomaly analytics with Watson looks at historical data to create a baseline of what is normal, where the workload interaction navigator has no prior context or knowledge of what happened within the environment. And Donald, yes, I will post the presentation right after I present this morning, so you'll have the slide deck that was here. So I'll post the deck. So the other kind of difference is in looking at Z anomaly analytics with Watson, we're looking at real-time data compared against the model in order to detect anomalies. And in that case, we're really looking for trends and patterns where those are used to forecast or detect potential issues. Whereas within the navigator, those anomalies are really used to correlate the different activities within the activity group and are really used, as Dan showed, to identify those cause and victim relationships within the environment. So just a couple of quick notes and to give Dan and his team some credit. So a number of IBM Z clients come to IBM when they have critical issues within their workloads. And in every single case, Dan and his peers rely on the workload interaction navigator to help get down to the root cause of what those issues are. We had a client that was looking at a response time increase that only happened around market open, so when the stock markets go and open. We were able to discover a lock contention that was the cause of that within DB2. Another one in a case where we're experiencing an increase in response times, and that was related to transient zip utilization spike. So we didn't have the right configuration in that case. So this is very good at finding the root cause of those very unique issues that might be going on with an environment that without this would be very difficult to diagnose. So we mentioned going through a rapid POC, and just in a client sending us data, Dan was able to go and find something that was going on in their workload that took them weeks and weeks to go and figure out. So they kind of use that as a litmus test or a gauge of what we can do. And there really is a lot of power within this solution. So just to kind of wrap up, the correlator is really that solution to the data challenge that I mentioned. It's smart, low-cost data that's time sequenced that we can go and look at with the navigator to really help diagnose a lot of those performance issues going on within the environment. If you do want additional information, please go out to the product announcement pages or the product pages to get additional details. I did mention that IBM recommends collecting the 98 subtype 1 records to help with first failure data capture. So there is a support flash that's out there, and there's a link to this. And I know this is something that Dan and his team strongly recommend for our clients, because there's a lot of valuable information in those records. We also have an IBM AIOps on Z Community where you can learn more about the solutions and a number of other things. So I think we have just a few minutes left, Anna, that we can open it up for last questions after we go through the feedback slide. So hopefully you guys found that this session was valuable. Please go out and leave the session feedback. Again, this is session 3BB. The QR code was there, and I know from the last time that I presented that question number 2, the answer for is the session too short, too long. If you thought this was appropriate, 5 is actually the right answer in this one versus the full sliding scale.
Okay. Yep. So session 3BB. Yep. Feedback. If you're using Bring Your Own Agenda, you can click on the feedback link for the session. Please give generously in appreciation to for the speakers and that amazing demo. And then I should have unmuted you. So, or rather, I've given you the opportunity to unmute yourself. So if you do have any questions, please feel free to ask them now, either in the chat or verbally. Okay.
I don't see
like, I was going to say, it doesn't look like we've got an uptake on the opportunity to ask questions. So if that's everything you want to say, I can end the session.
Yep, that's all. Thank you, everyone, for attending, and hope you found this as some valuable information.
Okay. Everyone enjoy the rest of GSE, and I'm sure I'll see you at another session shortly. Bye now.